We are talking about polymerization, and we'll kind of have one lecture on polymerization and another lecture on polymerization. I'm going to kind of sneak in a little bit of cross-linking because it kind of is in line with an assignment you all have to work on. We're going to talk a little bit more about the classification of polymers and how that kind of interacts with how the chains of the polymers are chemically interacting with one another. We're going to talk a bit about crosslinks, a bit more about crosslinks. We've really only looked at one example of crosslinks, maybe two. It was polystyrene. We talked about cross-linking polystyrene with divinyl benzene or benzoyl peroxide. If you look at the diagrams, the divinyl benzene is actually a shorter distance between chains, whereas using benzoyl peroxide, you have a lot of oxygens in a long line. So we're speculating that the polystyrene, based on the distance between the chains, is cross-linked to a stronger degree by divinyl benzene. So that was kind of the other example we've talked about. We're going to get into polymerization, and we might swing back to cross-linking as this lecture kind of comes to an end. Kind of a recap of what we've talked about previously, and it might not have exactly been last time because we've talked a little bit about the uses of polymers, and I kind of mixed up some of the lectures, some of the topics a little bit, but it's okay. We talked about kind of the configuration or conformation of molecules. And so isotactic, so we talked about that arene being on the, excuse me, on the polystyrene molecular chain. And we had syndiotactic and isotactic. And this is kind of an interesting thing to kind of stare at. I think I may have made a mistake with this. And I'm staring at it again. Okay, no, you have to stare at it closely. I'm so sorry. I stared at it, and let me bring up the pointer. So isotactic, everything is on the same side. So we had those polystyrene chains where we had the arene all on the same side. Here we have every other hydrogen coming out of the screen, and or if you want to look at it from the other point of view, every other hydrogen going into the screen. So they're not on the same side. Right, so here all your R functional groups, could be an individual atom, whatever, are all on one side. Here they're alternating. And so if they're all on one side, they're isotactic. If they're exchanging sides, they're syndiotactic. I actually had to pause and record myself pausing because it was hard for me to look at this diagram. So pause the video if it helps. But syndiotactic means they're on the opposite side. So if you remember when we had polystyrene and we had those arene rings, and sometimes we showed them all on one side, that's isotactic. And if we have them alternating or even almost random, it's syndiotactic. We called this conformation. Okay, so what was the third type? They call it configuration, so I'm assuming these words are used interchangeably. I kind of make assumptions on some of this stuff. After all, I'm a metallurgist, man. Configuration was this other one that we talked about. And so we had cis and trans. And these are also isomers too. So there's the kind of the example of Advil that people give. And I should put that Advil molecule up. So cis and trans, if we take a look at ibuprofen, and I said Advil, and there's a reason I said Advil. So there's two isomers of ibuprofen, S and R. One of them isn't quite as good for your body. And if you go to Walgreens or whatever, you can buy Advil, which is a name brand ibuprofen, or you can buy some generic brand. I've been told that one of these isomers of ibuprofen is a little more toxic than the other. And so the difference between the expensive ibuprofen like Advil and I believe Motrin is that they filter out one of these isomers. They've developed a process, and so that's what actually adds more cost to the more expensive ibuprofen. And so you might be better off buying the more expensive flavor of ibuprofen. But this is kind of just another example of isomers, and it's a kind of a physical property, if you will. So things have different physical properties. If you look at isotactic versus isostatic, the way that the polystyrene would crosslink would have an effect if you think about it, right? So anyway, kind of moving on. We talked about polymer classification in the past, and so I'm kind of recapping because anyhow, it's always good to kind of go over this stuff again because as metallurgists, we don't have this in our vernacular every day. Pretty much, we talk about cementite, I think, more than we talk about this stuff for sure. So we talked about nomenclature and that kind of thing. And you can kind of look at this. We had some examples of copolymers, styrene, acrylonitrile, SAN. I also talk about this in composites sometimes. So PAN, so polyacrylonitrile is where we just have a polymerized acrylonitrile group there. So SAN and PAN, kind of somewhat related. We've replaced, we've added in styrene for styrene acrylonitrile. So that's a copolymer. Tribok copolymer is SEBS, so styrene, ethylene, butylene, styrene. It's a tribok copolymer. Why? Because ethylene butylene is a rubber. And if you look at TEM micrographs, and I'll show you some micrographs of SEBS. I do a lot of research with SEBS in the lab. It's pretty much polystyrene spheres floating around in a ethylene butylene matrix. And so it's actually kind of neat. If you look at transmission micrographs of ABS, which I'll show you later in this course, you see that the acrylonitrile, butadiene, styrene, so there's butadiene in ABS, and they form actually rubbery spheres that float around in the matrix of SAN, actually. So if you add butadiene spheres, you get ABS, so acrylonitrile, butadiene, acrylonitrile, butylene styrene. So it's basically this matrix with rubber spheres in it, and that's all what ABS is from like a physical looking at it point of view. And I do a lot of polymer microscopy, and I may change some of the topics we talk about in class as we go on. I'll always kind of mix and match, but we'll definitely see some micrographs of this stuff. A bit more about cross-linking. So please watch the video Making Slime. Here's someone's hand, a former student from years ago making slime, and there's different variants of making slime. In the video Making Slime, we're using polyvinyl acetate. This is making slime from polyvinyl alcohol. So think about two flavors of cross-linking. So there's chemical and physical cross-linking, and the type of cross-linking and the amount of cross-links play a huge role in the physical properties of a polymeric material. So always kind of keep this in mind, kind of this structure-property relationship, which is a recurring theme in material science. If we look at linear polymers, and this is kind of the bowl of spaghetti, and I drew it with my finger using this kind of a tablet screen. So please forgive the lack of artistry, but hopefully you guys get the picture of what I'm trying to talk about. You have these linear polymers, or these chains just laying around. The individual chains, let's just pretend this is our chain here. They're connected with covalent bonds, so they're really strong, and we've kind of talked about this over and over again. This is unoriented if you think about it, so you can actually orient your polymers through a drawing process, and we can talk about this a little bit more when we talk about polymer processing. But this is unoriented. This is this blob of spaghetti, if you will, just kind of laying around each other. So individually, these chains are very strong, but in mass, you can kind of rip these chains apart. And that's like, you think about like a trash bag ripping and stuff like that. It's because of those van der Waals bonds, and they're kind of unoriented. But modern bags actually are getting oriented in terms of the polymer chain, so they're stronger, and it's kind of cool. So it's also, I always make the example of athletic jerseys as well. When you have branched polymers, they're chained with branches, and there's a covalent bond at this branch. And here's kind of an example. And we talked about low density polyethylene kind of having this branch structure, and they will have their own physical properties as opposed to something that has no covalent bond. You can't pack it in as dense because these branches are kind of sticking on each other. So think about actually throwing a branch together, a pile of branches versus a pile of sticks, and you'll kind of envision how things kind of pile up on each other. But there is covalent bondings for the chains in the branches, But the individual branched in chains, if you have a laser pointer, I don't know why I'm not using it. If you have the individual branches kind of linking up with something else that has branches, they don't covalently bond to one another. Okay, so there is some weakness associated with these. So you think about low density polyethylene. So it helps to kind of play around. So you can go get basically bottles of shampoo, and sometimes they're low density, sometimes they're high density, and squeeze them. So squeeze out shampoo or lotion. Lotion's another good one. Sunscreen, those kinds of packaging are generally one of the two polyethylenes, and you can kind of tell the difference between the two. When we have networked polymers now, and again, this is a recap of what we talked about before. I'm just kind of talking about it again, thinking about crosslinks in this point. And so here now, it's like this bowl of spaghetti, right? But now they're all cross-linked to one another, so you get some more rigidity. And the crash course chemistry had an example of PEX, and the gentleman in cross course chemistry, I mean, those videos are great, but he talks about when you cross-link polyethylene, you get PEX. That's true. He says you make it a thermoplastic. Well, that's quasi thermoset, excuse me. That's quasi true because I've actually been able to kind of soften PEX and put it together. We use it a lot in plumbing and making sprinkler systems and stuff like that. And a lot of homes nowadays, instead of having PVC in the walls, they're using PEX in there. I'm kind of a do-it-yourselfer. So think about it. Okay, so networked polymers. I didn't mean to go on this tangent. Networked polymers, the individual chains are cross-linked together. So think about it. So how do you think the number of crosslinks affects a material? Think about it, right? So we've talked about polymer chains moving, and when they move, they don't just slide, they also roll. Okay, and so when we bend something, stretch it, that kind of thing, these polymer chains are moving. There's kind of this viscoelastic flow, and we'll talk about that a little bit more. But think about it. How would the number of crosslinks affect the physical properties of a material? So if you look at this material, this is a cross-linked material, and this is rubber, okay? So rubber has one cross-link for every 500 to 1,000 carbon atoms, okay? So rubber. So think about it. One cross-link for every 500 to 1,000, carbon atoms. If we look at this, much more dense, a cross-link every 20 to 100 carbon atoms. And this would be a thermoset, okay? Something really stiff like epoxy, right? And so epoxy is one, very stiff. What's another good thermoset? I guess the aforementioned PEX, it's a lot more stiff as compared to polyethylene, but it's much more stiff. Thermosets are generally stiff. We think of them, rubber, we think of it as moving, and we'll talk about the entropy-based theory of rubber later on in this class. One cross-link every 2,100 atoms for a thermoset, much more stiff. We think of these as actually kind of brittle. And you think of Bakelite, and I don't know if you all have ever been exposed to Bakelite, but like old phones, my grandmother used to have this rotary phone, very big, heavy phone, very brittle plastic there. So think about it. So rubber, not very many crosslinks. So one crosslink for every 500 to 1,000 atoms. Rubber is bouncy. For a thermoset, one crosslink every 20 to 100 atoms. I'm looking around my desk for examples. Polymers are everywhere, obviously. So physical crosslinking. So this is thermoplastic. So we have a thermoplastic crosslink here, and so it's kind of this weak bonding. Entanglement is one. Hydrogen bonding also plays a role, but an entanglement can actually be a crosslink as well. And if I have this polymer chain and this polymer chain, and I kind of weave them together, they become entangled. And so entanglement is a weak form of cross-linking. That's reversible. Hydrogen bonding cross-linking is also reversible. And I've shown you this video before, but I'll show it again. So this is a temporary shape. We heat it up, and it's a shape memory polymer. And we'll talk about SMPs later. And we get the UTEP pick, yay. And we did this over and over again, and shape memory polymers actually undergo hysteresis, so it didn't quite get back to its peak glory, but we got pretty close. And we have other experiments. What's holding that temporary shape is basically a physical crosslink, like entanglement and or hydrogen bonding. And in this case, I believe it's actually entanglement. So it's a reversible crosslink. It facilitates the function of shape memory polymers, actually, or one flavor of shape memory polymers. There's many. We'll see it later in the semester. Chemical crosslinking, it's strong covalent bonds, and that's typically not reversible. How does this occur? And can we as scientists, material scientists, control where this occurs? So kind of ask that. And a chemical crosslink would be kind of like we saw with the divinyl. Sorry. All right. Well, let's talk about polymerization first. But the divinyl benzene, right, was one that we talked about for the cross-linking of polystyrene. So can we control where this occurs? So first we need to talk a little bit about polymerization. So polymerization, so Wallace Carruthers, very big time polymer scientists, early days of polymer science, and it's back when everything was called macromolecules, and that terminology is still used. Condensation polymerization, so there were kind of two flavors of polymerization, and you've seen the videos making nylon being a form of polymerization. And so this is making nylon. So you're combining these two chemicals, adipic acid and hexamethylindamine. And you've seen two experiments, I believe, making nylon 6,6. It's the more simple nylon to make. And there's different flavors of nylon, and that's just the amount of carbon chains in each individual groups. And so let's see, there's 6 carbons here. There's this kind of bond with this other macromolecule here. So another 6 carbons here. So nylon 6,6, byproduct is water. Another common flavor or common polymer that comes about as a result of a condensation reaction, excuse my words. Polycarbonate, like used in my glasses, plexiglass, if you will. Lexan is the trade name by, used to be GE Plastics, now it's SABIC, Saudi Arabia Basic Industries Corporation. And Bayer, the same people that make aspirin, also have their own flavor of polycarbonate called Macrolon. That results as a combining bisphenol A, this molecule bisphenol A, with phosgene, which phosgene is bad. Phosgene is a very toxic gas. It's actually what's released if you combust PVC. So you don't want to burn PVC or any really fluorinated, not fluorinated, halogenated polymer, if you will. But anyway, you combine bisphenol A with phosphine, I believe it's in a gas form. You get that, you get polycarbonate, which we just call it polycarbonate. I always called it polybisphenol A carbonate, which is kind of interesting. So they call it bisphenol A polycarbonate in this book. But anyway, you have this BPA, bisphenol A, has actually been in the news a lot because it used to be like Nalgene. You drink those Nalgene cups, but it leaches into the water. And so bisphenol A actually kind of leaches from the polymer, so you don't want to drink it. But anyway, that comes about as a result of a condensation reaction. And the byproduct is actually hydrochloric acid. So I don't know if I necessarily would want to be working with that. Addition polymerization, and we'll talk about it in a greater length. Addition polymerization, here's the example of styrene. You have these sigma and pi bonds. You break the pi bond, and you've seen an example of breaking of this type of polymerization. We're going to talk about it a lot more in the second lecture of polymerization as well. And you start getting chains of polystyrene, and this is similar for a lot of polyolefins. You have a ring opening polymerization as well, so you can combine this trioxane with acid. One of these bonds breaks basically, and it ends up instead of being a bunch of rings, you have a bunch of chains that link up together. This is also considered an addition reaction as well. Ring opening polymerization is also considered addition. So let me step back a little bit because I'm realizing I didn't really explain. This is condensation polymerization, where you combine part A, part B, and you can also make polyurethane this way. If even a can of great stuff is part A, part B in the can, and it mixes in the can, makes a spray insulation. Here we have two examples of mixing part A and part B to make a polymer. So it's condensation. And you saw in the videos where the gentleman sticks a stick in it and pulls out basically a string of nylon. And you can actually put that on a spinneret if you have like a big vat of these chemicals and make long strands of nylon. And it's a kind of a wet spinning process is what it's called. Addition polymerization, on the other hand, is where you have a bunch of molecules and you insert the free radical basically, or you have some sort of catalyst, if you will. And this free radical breaks the pi bonds and then causes the link up of these polymer chains. And we'll talk about this a little bit more. Addition polymerization. Polymerization of styrene is the example we give here. And excuse me, laser pointer, the example that we give here. And this is a ring opening polymerization of trioxane to get polyoxymethylene and another polymer there. But it's also considered an addition because you're taking the trioxane and just breaking it open so it can form a chain instead of a bunch of individual rings. The old naming, so this is the old naming. So typically you had condensation or addition polymerization, and that's what they called it. The old naming is not good enough. Okay, it can by today's kind of consensus in polymer science. So reactions lead to polymerization. Some addition and some condensation reactions share characteristics of one another, and so you have step growth is a reaction between any two molecular species, and chain growth. And so a monomer must have a reactive end group and it needs an initiator, and that initiator is generally a free radical. If you look at the table in the book, table 2.1, you have step polymerization and chain polymerization. And so you can kind of make I won't go through all of them. I encourage you to kind of look and kind of look at the differences. So you have step polymerization, and you have two molecules, molecules, so two mers coming together and forming a mer, and something has caused this basically. And so now you have a polymer has a dangling bond, you add another mer, you get a trimer, and boom, 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 all the way up to making an octamer. Chain polymerization is a little bit different. You have an initiator, and you have a molecule. So that molecule then has a dangling bond. So you have this initiator bonded to this molecule. This molecule, again, has a dangling bond, meets up with another mer, wants to stabilize this relationship, if you will, and it starts growing and growing and growing and growing and growing and growing and growing. It's a little bit different, okay, illustratively, and I get confused when I stare at these I's and O's on this table, but I kind of show it anyway. And they're chemically linked, basically. So polymerization is either stepwise or chainwise. Okay, so we have the stepwise polymerization, reactions between any two molecular species. Chain growth, again, you have to have a reactive end group. It needs an initiator. Okay, so we have this one molecule, this reactive end group. We don't have any reactive end groups here. Okay, so that's the difference between step and chain polymerization. But how does this happen? So functionality, as told by Thomas the train engine, there 2, there 4, there 6, there 8, hauling trucks and shunting freight. I think that's how it goes. Anyway, Thomas the train engine, functionality. Took me forever to make this animated GIF, but you have to have some functionality. And so I don't know if I posted one video. There was one video that was using an analogy of Legos. He was actually using the stack analogy. I use my child's old train toys to kind of show functionality. So we have this train car linking up with this car. Functionality. It looks actually kind of similar to what I've depicted as functionality. Animated GIFs, they're great. So these polymer chains coming together, functionality. So there's different types of functionality. Okay, so you have monofunctionality, where you have acetic acid and you have ethanol. And these can bond with a polyolefin to make PVA, basically. And so acetic acid and polyethanol, so monofunctionality. Difunctionality would be the esterification of acrylic acid. Kind of coming back to this, I didn't really explain it very well how this is how these are monofunctional. I kind of realized that when I clicked ahead. You can knock off a hydrogen off of here, and so you can knock off this hydrogen. It can then go with a vinyl group, so you can get vinyl acetate. And you can do the same thing here with ethanol. You can knock off one of these hydrogens. It'll link up with, you can replace one of the hydrogens on ethylene and make polyvinyl alcohol, basically. So it's monofunctionality. So mono, and I kind of have these kind of train link indicators showing mono functionality. So you can either have the C or the O or the gripper and the whatever. But you have two types of designations here. I'm kind of using this nomenclature. Mono to di, and so here this is an acrylic, and so instead of being H3C, it's actually H2C. And so you have a dangling bond, so it's functional on one side. You can esterify this, and so when you esterify something, you take the hydrogen off, you break the OH bond, or the bond between the oxygen and hydrogen, and you esterify it. So if I esterify it, I then have a dangling bond because it wants to have an extra hydrogen here because of the carbon, right? You want to have four bonds. So you have this dangling bond here. And then you have another dangling bond because you've esterified the acrylic acid, so you can link on both sides. So we have kind of three different nomenclatures that we could use to show difunctionality. So difunctional here, we have, again, my nomenclature for difunctionality. And on here, it would be the same on each side, so you could use either this one or this one to designate your functionality. And so this is going to polymerize via addition polymerization. So you knock off hydrogens off either side and they kind of link up. So it's kind of cool. Esterification of glycol, we can make this trifunctional basically. And we can make it trifunctional by esterifying each of these OH end groups here. And so we have dangling bonds on each side. So this can be esterification of glycerol. So esterify, if you think of polyester, it's because there's a process like this where you're knocking hydrogens off of OH groups to kind of create your material or your polymer. Here's a schematic representation. So how it polymerizes, you may guess. So this is going to make a chain, but this is going to make something else. This is going to make some sort of branchy structure, is it not? Because you can link up on 3 different points. And this table, this is from the Young and Lovell book. So you have linear polymerizations and branching polymerizations. And so if you have something difunctional and you combine it with something trifunctional, you're going to get this kind of branched network. And these guys use a similar nomenclature to what I'm using with my little inspired by my child's train. That's kind of where I got this from. To show that there are differences in how these things branch. And I'm kind of tripping over my own words. I think this is a good place to stop. Polymerization 1, mostly because I clicked ahead and I saw I ran out of slides. Oops. And so we're going to discuss particularly linear polymerization to a greater detail in the next lecture, Polymerization 2. Thank you very much for your time.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.